Hello, everybody, and welcome to today's SimScale webinar. The topic for this session is AI-powered design and optimization for valves and flow control. My name is Alex, and I'll be your host for today's session, and I'm pleased to be joined by Ajit Kumar, who is a senior application engineer here at SimScale, and together we'll take you through everything that you need to know about conducting this type of analysis using the SimScale platform. So, a quick overview of the agenda. Firstly, I'll introduce SimScale and the company's mission before handing over to Ajit. He will take you through the process of predicting simulation results using AI in the SimScale platform and demonstrating this using this particular example of a valve, and we'll show you the whole process from start to finish. Now, please do enter your questions into the GoToWebinar questions panel as we go along. Now, while we won't have a live Q&A after today's session, those questions will come straight through to us by email, and we'll be able to respond to you within a day or so. So what is SimScale all about? SimScale helps engineering organizations everywhere to innovate faster by exploring thousands of engineering decisions in seconds. So this is particularly relevant to today's topic of accelerating simulation predictions using AI. And if AI can be used to collapse that simulation, that analysis time, it means that engineers can then get access to a broader area of the design space and be able to make those design decisions much, much faster. And we see a big opportunity for delivering a transformative acceleration using AI tooling. So how does this work exactly in the SimScale platform? So we describe our AI tooling in two ways. We talk about physics AI and engineering AI, and we'll find out what exactly those terms mean in a moment. But that AI tooling is integrated natively alongside the traditional simulation of the CAE part of the platform, and that means that users are able to seamlessly, switch and blend between the two methods and the two types of methods as they wish. So let's take a look at the SimScale platform in detail. So of course, the first thing to know about it is that it is cloud native. It runs entirely in a web browser. It's also a collaborative environment. So users, multiple users, as you see there, can view the same simulation project or even edit the same simulation project at the same time. Very simple to share projects in between users or teams, and of course all of that data and all of the user, the user and the process is all managed directly in the SimScale platform as well. Now we're looking here at physics AI, so this is accelerating the computational part of a simulation result or simulation prediction. And physics AI allows you to predict simulation results instantaneously. So reducing runtimes from hours or days, or So we're also developing an agentic AI, we call it engineering AI, which allows you to automate the manual parts of the simulation process. And so if you combine the engineering AI and the physics AI together, then there's a possibility of accelerating the whole end-to-end workflow. And of course, going back to the traditional solvers, the traditional methods in SimScale, SimScale's mission has always been to cover broad physics. So we have flow, thermal, structural, and electromagnetics all in a single platform, all with the same user experience. So if you've learned one of those disciplines, it's very easy to move across into another. And it's also a scalable system. So we have automatic HPC provisioning. It's completely sort of transparent to the user. We don't need to worry about the infrastructure, the exact mechanics of how your simulations are run. You can run as many simulations as you need to concurrently, so at the same time, and it allows you to scale out your work and get the answers that you need sooner. So with that, I'm going to hand over to Ajit, who's going to really take us into a deep dive on the topic of physics AI. Over to you, Ajit.
Great. What does SimScale or what does AI bring to CFD or simulation domain, right? We want to quickly look at how this can work out and how we actually do it and what are the few advantages of using AI prediction for simulations. In this case, you can see we have taken a valve case, and to start with, you need the simulation data, right? All the AI algorithms are trained on existing data or new data that you can create. So if you have the simulation data, they are ready to be trained with an AI model within SimScale, because you don't need to jump between different tools to collect the data, pre-process it, and make it ready for the AI tool to actually read it. Everything is included and integrated within SimScale. And once when you have this simulation data, you can easily train the AI model and then start predicting the results in real time. Suppose if you have a valve case that runs within a few minutes or let's say 30 minutes or an hour, then you have a bunch of simulations that you can base the AI prediction with. Then you can start predicting the results within a few seconds. So the main thing to note here is if you have the simulation data, you can start predicting the results within a few seconds. That cuts down the runtime, the effort, and all the included activities in the background to actually get the results finally. That's just a quick overview of the AI models. But the other part that comes with SimScale is that since you're already on a simulation tool, once when you predict AI, if you want to validate or verify the results that you are predicting, you can simply switch between the partial differential equation based models or the actual simulation and run a simulation as well in parallel. So that's one advantage that you can also see in terms of verification of your models. I'll give a pause here and again remind all the audience to actually ask your questions in the question section, and we'll be happy to answer them at the end of this session. Let's jump into the main study for today. So it's a valve case. It's a globe valve where we have different operating conditions that we want to try. And with respect to the prediction, we are going to use a design space of different parameters geometrically and operating conditions wise as well. That is explained here, where you can see we're trying to actually build a database where we want to find out the flow characteristics like pressure and the forces on the valve for different valve positions. For example, here you can see we have the geometry variations that ranges from 2 millimeters to 24 millimeters on the valve position. And we have a supply rate of 0.02 kilograms per second to up to 0.5 kilogram per second. That's going to be applied for each of the valve position here. So in total, we have a database of about 117 design samples that we're going to run and use that for the prediction of flow characteristics later using the AI. Yeah. In general, there are a few numbers here on the screen, but we can talk about that later. So the training took about within 7 hours to actually get the data, process it everything on an on-demand GPU, and then give you back the AI model so that users can use that for prediction. Great. That's about the case that we're going to discuss, but usually simulations are a bit boring, right? So let's make it a little bit interesting by introducing two more characters into the play here. So we have two engineers. On the top, you can see, you can name him as Tom. I like Tom and Jerry, so I'm going to name him as Tom. And on the bottom, we have Jerry. And Tom is a structural engineer or a structural expert working in a valve industry. And he's been assigned with a task that to analyze the valve for different flow conditions and then see if the forces and the pressure values that he can get from the flow field can actually be applied for the valve design he's going to actually iterate on, right? That is his task. And something to note here is Tom has several years of structural analysis expertise, but the last time he ran CFD was in his university. So he's not that familiar with the CFD, and he would still like to use the data from a CFD-driven simulation to make sure his product is actually going to increase in performance. On the bottom, we have Jerry, who is a process or a systems engineer who also has expertise in reduced order models and system level designing. So her task is to actually collect the data from the simulations and plug it into a system level a design here. For example, you can um, imagine that we have like a process plant where there are multiple valves involved and a lot of other components involved. And right now we are trying to actually troubleshoot what will happen if the valve goes over range or at different valve positions, what's going to be the effect on the entire system. That's her task. And to help these two engineers, we're going to use SimScale's integrated AI tool and see how they can actually make use of simulation results for their data-driven design. Yeah. At this point, I'll quickly jump onto the platform and show you how you can work with SimScale with respect to Tom and Jerry here. Yeah, great. Then let me jump back to SimScale. And the moment you talk about SimScale, as I mentioned already, it's completely on a browser. To access SimScale, all you need to do is go into simscale.com on a browser and then log in with your credentials. Once when you log in, this is where you end up, where you can see all your projects that's been created by you or shared by someone else from the team as well. In this case, I have a folder named Valve AI, and I also have certain templates that I can start using as well. Let's imagine we put on Tom's hat and Tom comes in. He wants to actually do a valve simulation, which is a CFD simulation. As an intern, he wants to pick up the results and use it in a structural simulation, right? That's going to be his task. So to do that, we create a new project and name that as, let's say, valve analysis. And any project that you create within your account is private to you unless you share it with our support or one of your colleagues by entering their email ID. The moment you create the project, SimScale will opt for geometry input. But as Tom is not that familiar with the CFD workflow, he doesn't know where to start. Right? This is just a scenario that happens for many of the engineers on different tools on where to start the simulation. Right? To address that, SimScale actually has a templater approach where a new user can actually jump in and instead of starting from scratch, they can actually pick up one of the existing template and start working on that as well. And we're going to see how the workflow looks like for Tom here. So instead of importing a geometry, I'm going to import a template, a simulation template from the existing report. So I'm going to import a simulation. And if I look into my folders, I can already see I already have a valve template, right? This valve template can be built with the support of SimScale team or one of the experts in the company itself can control the template that can be shared with all the users. So right now, this template has been built by an expert, is shared to Tom for him to actually start using the CFD solutions. So I'm going to pick up one of the template, let's say the 18 millimeter opening of the valve. And when I import the simulation, I already have the respective geometry used in the simulation. And on top of that, I also have all the simulation settings done for me already from the template. At this point, all I need to do is verify if I'm using the right boundary conditions. For example, I know that I want to actually test the valve for 0.1 kilograms per second. So I'm going to enter that value here. And the moment you have your simulation template ready, you don't need to actually do the actual simulation. You can use the existing AI model to start predicting the values directly. And this is done by selecting the AI model that is respective for this valve. So in this case, I'm going to go with globe valve version 2. And within a few seconds, I'm going to get the results of the valve in terms of pressure and velocity as well. I'll give a few seconds for the results to load. And as I mentioned, the way we support our customers is also unique. And let's say if you have a template and you want to actually change something which you didn't know how to set up, right? You can directly open up the chat at the bottom right corner, send us a message stating, hey, I'm using this template and I don't know how to change this particular parameter. Then we are happy to jump in, help you then and there, where you can also share your project and we can take a look at the template and give you back our best practice guidelines as well. That's how the support works. And meanwhile, you can already see on the screen, we have the results already predicted using the AI model. So I can go back, I can start integrating the results. For example, I can range out the velocity and then see how the flow looks like. The flow comes in from this direction and then it goes through this valve. And the valve head is at 18 mm from the flow direction. So you can see there's a high velocity region on here. And if I hide this face, you can see clearly there are a few recirculation zones predicted as well. On the right, you have the main parameters that you get out of such a prediction. And that includes the forces on the valve. So you can define where you want to write out the forces already in the template, and the AI prediction will give you the values directly as a quantity here that can be copied and used further down the line. For example, we have the total force in X, Y, and Z directions. In addition to that, we also have the pressure drop according to the flow rate that we give here. For example, if you want to change the flow rate and see, let's say I want to use a different flow rate and I want to predict the results. All you need to do is change the boundary conditions and wait a few seconds for the new results to be predicted using the AI model. So let's wait for a few seconds and then taking a step back, Tom has to actually do some design modifications to the valve as well, right? He wants to actually check the valve at positions different than 18 millimeters as well, right? So we can focus on that quickly. So now you can see the second prediction is already there with a different flow rate without any simulation run on your template. When you talk about AI, there is an important question you need to address, right? So how can I actually believe the results that AI can give? So in order to address that, you can quickly verify what is predicted here is corresponding to what you have in your simulations. So let me go back to one of the existing trained data. So I'm going to go with 0.1 kilogram per second. And I'm going to bring up my actual CFD simulation as well. So let me quickly get the project. And here you can see on the left, we have the training data on which the AI model is trained. So this is the design space for the CFD database, right? So on the right, we have the AI prediction already written. So in this case, let's open up the 18 millimeter model and run down to the flow rate that matches our predicted result. So here we have the 0.1 kilogram per second. Let's go into that and post-process and see whether the prediction is good enough for me to actually make design decisions on that. So the results have been loaded now. On the left, you have the CFD simulations. On the right, we have the AI prediction here. So on a general scale, you can see the flow fields look pretty much closer, right? We have already also have these recirculation zones predicted and also the accelerations on the other side of the valve because of the flow rate. There's also a bit of flow separation happening here that is also predicted here, and a bit of acceleration here at the bottom as well. So in general, this is how you can verify if your prediction is good enough. And if you're confident using that, then you can start using the prediction AI predicted results for your design iterations to be made. Right? This is the verification stage that you can do. But as you can see, you're not limited to the flow rates that have been trained. You can also go on a random flow rate within the range and start predicting the results. So I'm going to go back to my prediction here. And now I can actually, now that I'm confident, I can go ahead and try a different flow rate as well. And on the right, you can see there was a confidence meter. That gives you a good indication of how close the AI results are to the trained CFD actual data, right? This will give you a good insight on the first check on how good the results are. And on top, if you find that this percentage goes down because you're using some value out of the range, which is not used for the training, or the geometry is completely different. For example, you're using a valve model, valve AI model for a pump, for example, then the AI doesn't know how to handle that, so the confidence levels go down. In that case, you can go back to your experts or contact SimScale and say that, hey, my AI prediction is not good enough for me to use. So what can we do? In that case, you can run more simulations or try to actually add more to your design space and retrain your AI model directly within SimScale. This will help you improve the AI prediction as you go. Yep. Great. Now we have seen a quick verification of CFD versus AI. And now we want to use the AI prediction for a different model or a geometric variation, right? I'm going to close the AI prediction here. And now I can try to import a different geometry. So I'm going to go back to my template folder and say, I want a new geometry which has 3 mm opening, which is not part of the AI training database. So this is a completely new geometry that I want to actually see how the performance look like, right? So I have my 3 mm model. Let me quickly check if I have the geometry. Okay, it seems like it's a 7.5 mm opening of the valve. So shouldn't be bad. Let's go with a 7.5 degree opening of the valve. And now I have all my boundary conditions already imported, and I can directly go ahead and use the AI prediction to see a completely new model on how it behaves in terms of flows and the pressure values. Yeah. While the simulation is, the AI prediction is running, Tom had to actually do a structural simulation as well based on the AI prediction or the results from the flow analysis, right? So now you can see it's a new model. We have about 86% of confidence. So it's good enough for me to make design decisions. So I can go ahead and say, hey, I have a pressure drop of certain value and the forces on the valves are of certain value. I can quickly copy that and use that in a structural simulation, right? Again, I'm going to import a simulation, a structural simulation this time, and import the values that I've predicted from the CFD run. So I'm going to go with a flange structural simulation. And now with the setup that I have, I can go back to my internal pressure, simply change whatever I have predicted here and say I have a 15 bar pressure internally, and I can start a new structural simulation based on the results. The advantage is that you have both the AI prediction and this high fidelity simulation accessible under the same hood. And this can help users to actually switch between them depending upon your requirements. So I can predict a CFD simulation, but I can run an actual FEA simulation in the same project and get the required results at the same time. And that ends the task of Tom. Now he can actually wait for a few minutes and then take a look at the FEA results and see if his valve actually performs better in terms of the flow pressure and how does it actually handle in terms of structural integrity as well. Great. This is just a quick example, but as I mentioned, this is not explicitly or specifically for valves. You can also have a pump case or a different product that can be trained with AI and start predicting results within a few seconds. Great. I hope this gave you a quick introduction on how you can use AI model in predicting the results and how you can use them for a different analysis as well. But the second use case is that we have Jerry, who is a system level design engineer who wants to use simulation results in a process control or a system level analysis, right? For that, SimScale also provides this AI prediction capabilities using the API, the application interface, where The users doesn't even need to actually use the GUI, but actually have a simple Python script where they can actually start predicting and copying the data that you predict into a system level design. That way, the system engineer who doesn't have any experience with simulation or 3D simulations in general can even use a completely built template, extract the results, use them in a system level design. And that's what you have seen here, right? So now Jerry also has the predicted results within a few seconds. This is really important because for a process or a control engineering, you would like to actually change the variables or the parameters to see how the system behaves in a continuous manner. And Jerry can now get results within a few seconds, plug it into her system model, and see how the system behaves. So these are two sample cases where the predicted results can be used. And there are multiple other use cases that we can discuss. If you have anything specific that you want to try, let us know. We are happy to actually talk with you in person as well and try to understand how you can use these kind of predictions in your design process. This is not specific for valves. You can see we have cases where we ran a pump model with different geometric variations, including number of blades or blade thickness or blade angles. And in total, we ran about 180 variants that took about 2 hours because we're running everything in parallel on SimScale. And there's no pre-processing time for the data to be trained for an AI model. So within a few hours, you can actually get the AI prediction ready, which can be used by your engineers to actually make design-informed decisions directly. We've also seen from our customers that some use this AI prediction for marketing and sales, or if you're on a client site and you want to actually present something that you have designed and get their confirmation, instead of running the actual simulation that might take hours, you can directly use the AI prediction and show them the results and get the confirmation, and then come back and run a CFD verification if required within the same platform. There are other examples where we have done the muffler study, where we had about 200 different data samples run within 2 hours, and then again used in AI prediction. And also on the structural side, you can also do this not just with flow parameters. You can do a structural simulation and also start predicting the structural integrity or the stresses in your components or your assemblies as well.
Thank you, Ajit. That was brilliant. Very nice demonstration. So maybe just to wrap this up, I just wanted to run through one last slide, which is just sort of putting, I guess, putting what you've just seen in a bit of context and explaining how this is different on the SimScale platform compared with using other tool sets. So the traditional sequence of steps that would be needed to generate one of these AI surrogate models from simulation results goes like this. So data, using more traditional tools, on-premise tools, tends to be a bit more fragmented. So it's not all in a central repository in the same way that it would be on SimScale, but it's typically kind of scattered around on different machines or different clusters, maybe in the cloud or maybe on premise. The data needs to be collected together. It needs to be pre-processed. Then it needs to be fed into the AI model training process, which should typically be another tool. Often that's done by a third party. It would need specialized hardware, GPUs, and so there typically is a fair amount of kind of complexity to be navigated in order to do that, to go through that process. And then once the model is generated, there's there may or may not be any management layer that would allow you to sort of release those models to colleagues or teams, or to control the versioning of those models. And then when it comes to actually using the model and running those inferences, oftentimes we find that then engineers are having to use maybe two different environments, sort of one using a simulation environment to view simulation results, and then to use another post-processing tool in order to view the AI predictions. And that kind of makes it awkward to compare the two, and awkward for those two results to complement each other as well. So this is what we're trying to change with the SimScale platform. So we do everything in a single sort of vertically integrated environment. So everything's happening in the same place, from that data generation to the data preparation and the model training and the model management. As you saw in the demo, the models can be versioned, they can be released with full access control. And that all takes place in a single integrated environment, which makes it much more seamless to do. It also means that if you've been using the SimScale platform for a while, you actually already have probably data which is ready or in a good state to be used for AI training, because all of the simulations you've ever run will still be there stored in the cloud. And then finally, once you have created an AI model and you are using it to create those instant predictions, you can then flexibly use it together with your traditional PDE solvers in a single interface. You can very seamlessly switch between the two. You can perform design explorations, maybe using the AI model, and then you can go and validate a single click. You can then validate using a full solve as well. So that concludes today's session, today's presentation and demo. I hope it was useful for you. Thank you very much for joining us today. And as I mentioned, if you do have questions, please don't hesitate to drop those into the questions panel in your GoToWebinar window, and we will get back to you shortly. Otherwise, until next time, goodbye.